Hi everyone, I'm Nika, and today we're continuing our journey into understanding neural networks. In this session, we're going to talk about one of the most important components of a neural network, the activation function. We'll explore different types of activation functions such as sigmoid, ReLU, Leaky ReLU, Tanh, and more. We'll also discuss why we need them, what the pros and cons of each are, and even how to write a custom activation function if the built-in ones don't suit your needs. Now, let's get into the content. First question: why do we need activation functions at all? To answer that, let's remember the structure of a basic mathematical neuron. We have input signals, each multiplied by their respective weights. Then, a bias term is added. This sum is the input to the activation function, which produces the neuron's output. Without the activation function, this is just a linear transformation. It doesn't matter how many layers we stack without activation, it's still a linear model. The activation function introduces non-linearity, which allows neural networks to learn and represent complex patterns. Furthermore, activation functions help limit the output of a neuron. Without them, the output could range from negative to positive infinity. This isn't always desirable. Sometimes we want to suppress the signal entirely or constrain it to a fixed range. Biologically, if a neuron doesn't receive a strong enough input, it doesn't fire. Mathematically, we need the same mechanism if the combined input is too weak. The output should be zero or close to it. Activation functions give us that control. The dataset we'll be using today is Fashion MNIST, a popular dataset of clothing images. We're loading it from Keras, and it gives us a training and testing set. Our target labels range from 0 to 9, representing 10 different clothing categories like t-shirts, trousers, sneakers, and so on. However, we need to convert these labels into binary vectors for classification. We do that using the categorical function, which gives us a one-hot encoded vector for each label. We also normalize the image pixel values from the original from 0 to 255 range to the from 0 to 1 range by dividing by 255. This helps the network learn faster and more effectively. Now that we've prepped the data, let's return to activation functions. Let's start with the simplest one, the linear activation function. It's just the identity function. Output equals input. While it might seem harmless, it comes with some serious drawbacks. First, its derivative is always 1, no matter the input. This means gradients never change, which isn't ideal for learning. Second, stacking multiple linear layers with linear activations is pointless. The whole thing reduces to a single linear transformation. So, linear activation adds no complexity and is rarely used on its own. Now let's look at the sigmoid function, one of the most widely used activation functions historically. It maps inputs to a range between 0 and 1. If the input is 0, the output is 0.5. If the input is large and positive, the output approaches 1. If it's large and negative, it approaches 0. This bounded output range is a major advantage. It introduces clear output boundaries, making sigmoid great for probabilistic interpretation. Also, around the input range of -2.5 to +2.5, the output changes quickly. This is where learning is most effective. However, sigmoid has a critical weakness: the vanishing gradient problem. If the input is too small or too large, the gradient becomes almost zero, meaning the network stops learning. This is especially problematic in deep networks. To really feel the impact of vanishing gradients, try this. Build a deep network with several dense layers, say 5 layers, decreasing in size from 128 to 10 neurons. Use sigmoid activations throughout. Now let's declare our dataset. We will output it in small pieces of data because we have a lot of data, and the neural network cannot work with all the data at once. Therefore, we can give the data batch by batch in such small chunks. Each chunk will consist of 64 images. To do this, We can create small slices, pieces, declare our dataset slices, and additionally shuffle them to add even more randomness. We can iterate through our dataset, retrieving chunks of batch size 6.4. No, we can move on to training. We will go through two epochs, not many, just enough to understand the vanishing gradient problem. You'll notice that during training, weights in the deeper layers barely update, the learning gets stuck. This happens because gradients vanish as they pass through each sigmoid layer. In cases like this, sigmoid might not be the best choice. ReLU rectified linear unit, for example, often works better for deep networks because it doesn't suffer as severely from vanishing gradients. So, what's the takeaway? Activation functions are essential for making neural networks powerful and expressive, but not all functions are equally effective in all scenarios. Linear activations lack flexibility. Sigmoid is intuitive and useful in small networks or binary outputs, but can cause problems in deep networks. There are many more functions out there like ReLU, Leaky ReLU, Tanh, and each has its own trade-offs. Understanding their behavior, especially their derivatives, is key to designing and training effective neural networks. In our next sessions, we'll look deeper into these alternative activation functions and even learn how to create custom ones for specific tasks. Thanks for sticking with me today. See you next time.